Hey guys, I hope everyone's doing well. Today is Monday, so it's a little bit different than usual. Hopefully some of you guys will sign in and we can verify that the audio is working, although it looks like it's working from my end. So, that isn't going to work. Let me fix this. We need to do that. And we'll go here. Trying to make sure everything sets up. How are you guys doing? If anyone has any questions before we get started, the exam 2 review questions were posted on Canvas. Oh, thanks, Catherine. It's always nice to know that everything's working. This is not the usual place. It's not the usual setup, but I think everything works or will work well enough today. So, how's your studying coming? Is everyone ready? If you have any questions before we get started, let me know. If you don't, in just a second, we will start with the 7 review questions that we have. So if there are topics that you have questions about, you can drop it in the comments box. If there's anything else or really any questions you have, I am happy to answer those. So, since some of you probably are considering asking, the exam is very similar to last exam. Exam 1, there will be some number of questions. There will be an embedded periodic table. I haven't finished writing the exam, but it'll be between 20 and 30. You should expect it to take roughly the same amount of time and to show all of your work for partial credit as you did just the last time. So it's between 20 and 30. Some of them are long mathematics. Some of them will have ABC parts. Some of them will just be do this one thing. Any other questions about the exam or about the equation sheets or anything else before we think about answering any of these questions? So far, it doesn't look like there are any, but as always, if there are, So Zara asks, how will we know when there will be no reaction between compounds? So no reaction means one of two things. Either when you mix two, so let's talk about no reaction in terms of if you were to pour an insoluble compound, like you try to dissolve something that is solid and stays solid into a liquid, nothing will happen because the solid rocks stay as solid compounds. So that's option 1. Option 2 is that in a metathesis reaction, the 2 new products are both soluble. So when you do that, no reaction occurs. So those are really the only 2 ways that we see that in Gen Chem 1. There are some other ways in other types of chemistry classes where that could happen, but by and large, that's really the only 2 ways that will happen here. Did that answer your question, or are you looking for more information? All right, I think this is going to work. Actually, I have no idea if this is going to work today when I try this. And does work, except we cannot see the question. So let me see if I can fix that. No, stink. This, hold on. Yeah, that in fact is not any better. So unfortunately, because of the way this is set up, what we will do is we'll try it up at the top. It's just I can't seem to get it to work any better, but I'll put it in the comments today. So we're going to start with this question, number 1. And so this question says, a scientist mixes together 25 mils of 0.276 molar sodium carbonate and 91.2 mils of 0.463 molar lead-3 nitrate. What is the balanced equation and what is the net ionic equation? So as we think about that, the way that you're going to set this problem up is you're going to start by writing out your reactants. So your reactants are sodium carbonate, which is Na2, CO3, and that's aqueous, plus lead-3 nitrate, which is PbNO3, 3. And then we're going to need to predict a product. So this is the metathesis reaction. So metathesis is the scientific equivalent of a do-si-do. And so we know that both of the anions are going to switch cations. And so I personally like to set this up by writing out the complete ionic equation first and then going from there. So we're going to have Na plus aqueous plus CO3 2 minus aqueous plus Pb3 plus aqueous plus NO3 minus aqueous. Now, I have left off the stoichiometric coefficients so that when we balance the equation, we can go back and add those. So when we swap partners, we know that the sodium and the nitrate are going to be create a new compound. So we're going to have sodium nitrate, and then we're going to have lead-3 carbonate. So lead-3 has a 3 plus charge, carbonate has a 2 minus charge, so we are going to do Pb2 CO3, 3. So there's two things. Oh, you can't see that at all. Sorry about that. So when we think about this, one of the things we need to think about is what are the states of our products. So you would want to have access to a solubility table. And so when we look at this, we know that nitrate compounds are always soluble, so that would be aqueous. And when we look at carbonate compounds, the only ones that are soluble are ammonia as well as the alkali metal cations, which are basically that very first column. So that's going to tell us that this lead carbonate is going to be solid. So we also need to balance this equation. And so when we look at this, we can start with balancing the lead carbonate. And so in order to balance that compound, we need to put a 2 here, and then we're going to put a 3 here. And when we do that, that now means that there are 6 sodiums, 3 carbonates, 2 leads, and 6 nitrates, which gives us a 6 in front of this. So your balanced chemical equation must be balanced. It must have states. So we've answered the first part of this question. Now we need to finish the complete ionic, which is how we get the net ionic. So on the product side, we also have the 6 Na plus aqueous plus 6 nitrate molecules aqueous. And then the lead carbonate, Pb2 CO3, 3, is a solid, and it stays together. So in a complete ionic and a net ionic, the solid doesn't come apart. So you can think about that as it's creating a rock. And when you add rocks to water, nothing happens. The rocks, in fact, stay the same. So now we can cancel out anything we see on both sides. The sodiums cancel, the nitrates cancel, which leaves us with, our final net ionic equation, which is 3 CO2, CO3 2 minus aqueous plus 2 lead 3 plus aqueous is going to give you Pb2 CO3, 3 solid. So when we think about a net ionic equation or the complete ionic equation or any type of metathesis reactions, this is how we're going to set that up. So what questions do you have before we move on to the next one about this type of equation? And as always, if you don't have any questions, you can go ahead and plop that into the comment box and we'll go right ahead and move on to the next one. Nice, Nicole, that's great news. Sweet. Great news, Catherine. Okay, well, let me copy this one so I can drop it into the comment box since it's going to, maybe we can fix it by doing that. Maybe we're lucky. I might have solved all of our problems today, but legitimately it's not participating like it is, but it's a little bit better. So Jordan asks, while I was setting that up, do you want us to label the equations? You don't need to. I'll be able to tell the difference between the two, but extra labeling or extra boxing of your answers is not a problem. Destiny asks, do you have to show the complete ionic equation when you share your work? If it asks for it, yes. If it doesn't, you don't necessarily need to, but it may help you do that. So if you do not need it, then you don't have to, but it will specify. If I'm asking for that, it will say it in the question, because I hate to ask you to grade you on things I didn't ask for. So that's definitely not what's going to happen. So the second question is, what volume in milliliters of a concentrated solution of sodium hydroxide, 6 molar, must be diluted to 200 milliliters to make a 0.880 molar solution of sodium hydroxide? So in order to do this, this is a dilution problem. The words that you wanted to look for are dilution, solution, stock. Those tell you that this is a dilution. And so we know that a dilution equation is M1 V1 equals M2 V2. So there we go. Sorry about that. So we know that this is true. But now we have to figure out how all of these values in the problem interact with one another. Because if you get them backwards, you're not going to get the right answer. So M1 V1, M2 V2. So it turns out that it says what volume of a concentrated solution, 6 molar. So we know that that one's going to be 6.00 molar. But the volume equals question mark, so we don't know that. But the volume of the second solution is 200 milliliters. And the molarity of the first solution, or the second solution, is 0.880 molar. So in this case, we can rearrange the M1V1 equals M2V2 equation to solve for V1, or you can just plug in your answers. Either of them is fine. So V1 equals M2V2 over M1. And when we plug that into our calculator, what we're going to see is, or first we'll go 0.880 molar multiplied by 200 milliliters divided by, whoops, not 0, 6.00 molar. And this equals 29.3 milliliters of our stock solution would be added to a final volume of 200 mils. So when we think about this type of equation or this type of question, what questions do you guys have? As always, if you have none, you can go ahead and drop that right in the comment box. I think it's over there. I never really know. So what do we think about dilutions? Dilutions are pretty easy, in my opinion. Thoughts, questions, what do you guys think? Thanks, Nicole. All in all, this is pretty easy. Don't forget that your sig figs will come back. I mean, we never really left them, so it's not like they're new and different, but we're going to come back to this. So far, it looks like you guys are all doing pretty good with this one, so we will move that. Oh, Angela, I think so too. That's great news. All right, so let's see if I can copy. We're trying to get it. There's a way that you can make these question boxes like smaller, but legitimately it's not participating today. So we're gonna just do our best. and I will drop this into the comment box. Hold up. Technical difficulties. Oh man, that means it's too long. Hold. All right, now after all that, we can start to think about this problem. So this problem, number 3, a student finds a bottle labeled sulfuric acid that does not have a concentration. To determine the concentration of the acid, they set up a titration using 0.876 molar potassium hydroxide. They used 35.27 mils of the base to reach the equivalence point of 28.19 mils of acid. What is the concentration of sulfuric acid? So the first step is always going to be a balanced chemical equation, okay? So in this case, we're gonna start with that. And so we're gonna take our sulfuric acid, which is H2SO4, plus potassium hydroxide. And in this case, we're going to mix those together to get potassium sulfate plus water, which is kind of, perfect. So in this case, when we look at the balanced chemical equation, we know that the potassium hydroxide or the potassium sulfate requires 2 moles of potassium. So we're going to drop a 2 here and 1 here. Sorry, this app is a little touchy. So in this case, now we have the sulfuric acid and the potassium hydroxide. Then we're going to create potassium sulfate and water. So once we have this, now we can start to do the math, and the balanced chemical equation is super important. That way we know the ratio of acid to base. So in this case, we're going to start, we want to determine the moles of base. So we're going to use the molarity, which is 0.876 moles in 1 liter. Now I just took the molarity and split those units out, and I did that because it's going to allow us to manipulate that. We're going to multiply that by the volume in liters, which is 0.03527 liters. When we plug this in our calculator, we're going to get 0.030897 moles of KOH. So you may be like, you're using way too many significant figures. I always like to tack on a couple extra so that when we get to the end, we don't really have questions about extra digits. So it's better to trim them off at the end than cut them off early. So from here, we know the moles of potassium hydroxide. Now we're going to convert, using the stoichiometric ratio, moles of potassium hydroxide to moles of sulfuric acid. So we're going to take our 0.03879, nope, 97, there we are, moles of KOH times 2 moles of KOH for every 1 mole of H2SO4, and I'm going to double check this since I made a transposed note. That equals 0.015445 moles of H2SO4. So from here, now we know the moles of acid. We also know the volume because it comes in the problem. So in order to determine the concentration, we're going to take our 0.015445 moles of H2SO4. We're going to go ahead and divide that by the volume, which is 0.02819 liters. And that gives us a 0.54801 molar. But we need to check our sig figs. So in the problem, the least number is 3, and we basically just multiplied and divided a billion times. So once we add our sig figs, That's going to give us 0.548 molar. So what questions do we have about titrations, which are probably one of the not the most, but one of the more complicated calculations because it really takes a bunch of different steps. So do we have questions? What do we think? Do we like titrations? As always, if you have none, you can go ahead and drop that in the comment box too. Great news. So far, it sounds like these are going pretty well today, which I always like to hear. It's good news. A lot of times students, I don't want to say they prefer the limiting reactants, but I find that under the right conditions, titrations are in fact way better than limiting reactants. So let's think about the next one. We will see if we can make this work. So Jordan asked, are we going to be asked which is the titrant and which is the analyte? No, you should be informed which is the titrant and which is the analyte in all situations, at least on the exam, or really any material that I provide. But yeah, I'm not going to ask you that on the exam. So in our next question, it's going to ask, number 4, the surroundings do 98.1 kilojoules of work on the system, while 89.4 kilojoules of heat is lost to the surroundings. What is the change in energy for this system? So this question comes out of chapter 5, and it is delta E equals Q plus W. So just a simple-ish addition question. But the trick is we need to figure out what the sign, we need to assign the signs for Q and W. So Q and W. So Q is heat. And so in the question it states 89.4 kilojoules of heat is lost from the surroundings. So if the heat is lost from the surroundings, heat is gained by the system, so that means the heat is going to be positive. 89.4 kilojoules. And the work, the surroundings do work on the system, so when work is done on the system, W is also positive, and that is plus 98.1 kilojoules. So then we're just going to set this up as Q plus W, and that equals 89.4 plus 98.1, and this is 187.5 kilojoules is the change in energy. Let me make sure I'm checking this over because I find that the heat and W assigning of the signs can also be a little tricky. So the surroundings do work on the system, so work will be positive, and 89.4 kilojoules of heat is lost from the surroundings, which means it's into the system, which makes it positive. Questions about this topic? do we find this? Nice. I think this, if you have the table, this is not tricky. I do find that I always have to kind of sit down and really think through this calculation because sometimes you can miss a word or a surroundings or an on or by, but any other questions? Although it doesn't sound like many. So I will start getting all of the rest of these set up in maybe a way that we can see them. Catherine, I am with you. I will be honest, I assign the signs, I don't want to say wrong frequently, but occasionally I get them backwards or just kind of have to really think about it. So don't ever feel bad about that. Perfect. Okay. Look at that. This one's going to work. Okay, so in our next question, also from chapter 5, it says, in order to rapidly cool a water bath, 87.12 grams of a cooling compound is dissolved in 518.98 grams of water. If the water bath started at 145.2 degrees Celsius and was cooled to 42 degrees Celsius, and the specific heat capacity of the solution is 4.184 joules per gram Kelvin, how much heat is released? I'll come back to your question at the end of this one, Jordan. So in this case, we know that this is it's like a coffee cup calorimeter. So we're going to have Q equals negative M C sub S delta T, as long as that's of the water, which is what we're measuring. So now we just need to pretty much figure out the values, and then we can put it into this equation. So in this case, we are looking for M, C sub S, and delta T. So M is going to be equal to the total mass because we're looking at the total system. So we're going to have 87.12 grams of the cooling compound of unknown composition plus 518.98 grams, which is going to give us 606.10 grams. From here, we also already know that C sub S equals negative 4.184 joules per gram Kelvin, and delta T is going to be from T final minus initial, and so it is 42 minus 145.2 degrees Celsius. And so when we plug this in, we just need to make it a little smaller, we get negative 103.2 degrees Celsius. And so I'm going to I'm not going to trim this back based on these significant figures just yet, but I will at the end. So now that we have this, we're going to go ahead and plug this back into our calculator. So Q equals negative 606.10 grams times 4.184 joules per gram Kelvin. Oh no, I'm out of space. How are we going to fix this? I know. And we're going to also multiply this, I'm sorry for the messy work, times negative 103.2 degrees Celsius. And now we're going to plug this all into our calculator, and we're going to get 261707.19 joules. So in this case, it doesn't ask for it in kilojoules or joules, so you can leave it in joules. If it doesn't specify, I will also take it in kilojoules. But we need to trim this back to the least amount of significant figures, which is in fact 2, based on the 42 degrees. And so once we do that, we can get an answer, which is 1, 2, 3, 4 joules, or you could have written that 2.6 times 10 to the 5th joules, or you could have turned that into kilojoules. So I will make this a little bit smaller so you guys can see it. while I answer Jordan's question. So in reference to number 4, which was the delta E equation, Jordan asks, will we ever be given the change in energy and asked to find Q or W? We certainly can. I have asked that in the past. I know Alex asked that question, but as long as you're given 2 of the 3 values, you could do that, and whatever value would be that answer. So if you solve for W and it is negative, then the sign of that is true. Does that make sense? So Catherine asks or makes the statement that C sub S is negative. It definitely shouldn't be, but it does look like it is on this. So I will go ahead and, since I actually have the ability to erase things, make that go away. Hopefully that was just like a stray mark. It definitely shouldn't have been negative. Sorry about that. Other questions about coffee cup calorimeters? So far, it doesn't look like it. So while you think about that, I will go ahead and add up the next one. We'll make this size font. We will hit, oh wait, gotta copy that. And so the question we're going to look at in this case, hold on. I'm gonna need this to like actually work today. Struggle is real. So okay, so in this question, it says when an electron is hit with a photon of light, it is excited from the n equals 3 to the n equals 7 state. What is the wavelength of light that hits this photon? Use 3 sig figs. And then it says draw this transition as well as the return to ground state, which is n equals 1. And when I solved this a little bit earlier, I realized that it doesn't specify the units, so I've added those both into this problem and into the comment box. That we want to answer the wavelength in nanometers. So when we talk about wavelength of light, it's almost always in nanometers. So the first thing I'm going to do is draw this transition, because I think that that kind of helps us get the idea in our mind about what's happening. So the n equals 1 state, 2, 3. So we have n equals 1, n equals 3, and n equals 7. So our photon of light will be excited from the n equals 3 to the n equals 7, and then it is going to decay or emit light when it falls back from the n equals 7 to the n equals 1 state. A couple of things about this. These lines really need to be where they decay in size, basically by half. They basically decay in order of about a half. Now you don't need to get out a ruler or anything, but you do need the ability to make a graphic that looks like this. So from here, we can now start to solve this question. So the electron is hit with a photon of light. It's excited. So we know that we're going to start by calculating delta E. And delta E is equal to, delta E equals negative 2.18 times 10 to the negative 18, 1 over n f squared minus 1 over n I squared. So we know that the initial state is n equals 3 and the final state is n equals 7. So we're only asking about the first transition, definitely not the second transition. So we can plug this into the equation to where that equals negative 2.18 times 10 to the negative 18, 1 over NF, which is 7 squared, minus 1 over 3 squared. So when we plug this into our calculator, we get 1.977 times 10 to the negative 19 joules. Now you might be asking yourself, what happened to the negative sign? So you'll notice when you plug this into your calculator, negative 2.18 multiplied by that clause, the negative sign goes away, which is great news. So from here, we can then go on to use these equations. So E photon equals H lambda. Now, in this case, E photon also equals delta E, because the photon of light is equivalent to the decay in this state. So sometimes when we look, or the difference, in some cases during emission, so this is absorption, during emission, E photon is equal to negative delta E. So this is the other kind and is in fact also opposite. So we know that the speed of light is equal to, it is not equal to Planck's constant, it's equal to the wavelength times the frequency. So I'm going to resub into this equation to get hc over lambda, where lambda is the wavelength. And so lambda equals hc over E photon. So from here, we can start to put stuff into this equation. So we're going to have some space constraints, so I'm sorry you can't read both, but I can actually just make this go away, and we'll pull it back up if we need it. So now we're going to plug this into our calculator, where 6.626 times 10 to the negative 34th joule seconds is Planck's constant times 2.998 times 10 to the 8th meters per second, divided by the energy of this photon transfer, which is 1.97 times 10 to the negative 19 joules. And I'm going to go ahead and tack on the conversion out of meters into nanometers. And so we know that in 1 meter, there's 1 times 10 to the 9th nanometers. And when you plug this all into your calculator, you would get 1004.8 nanometers. And so in order to make this have 3 sig figs, it would be we're going to have to put that into sig figs. So it will be 1.00 times 10 to the 3rd nanometers. So it's not 101 or 1.01 times 10 to the 3rd nanometers, because 4 and up round, or 4 and down round down, 5 and up round up. So we can't round the 0.8 to be 5 to round up. That's too many roundings. You can only round one thing at a time. So as we think about these questions, which I do understand are long and involved, what questions do we have about this calculation? About the methodology, about how it works? We've done a number of examples. It was your weekly assignment. How are we feeling about this type of calculation? Does it feel easy? Do we wish that we could do this 100 times in a week? Seems a little excessive. What do you guys think? So far, it's not looking like a lot of you guys are having questions about this one. Ooh, Catherine asks, how do you know when to manipulate which equation? So most of the time, Catherine, when we think about these types of equations, it's all, in this case, all going to be the exact same manipulation. So Angela concurs that it's hard to manipulate the equations. So one thing to think about, you also don't have to manipulate this equation. You could have, so I'm going to make this get way small. So you could have also taken your E photon equals delta E equals Planck's constant times the frequency. Then you could have solved for the frequency, which in this case, I'm going to make up a random value of, I don't know, 1.257 times 10 to the negative 18. So in here, once you do that, then you can go ahead and plug this into the C equals lambda times nu, and then go solving for lambda to where lambda equals C over V. So I only like to use my calculator once. That's a me decision. You are not obligated to also partake in that. So that's what it is. So the other questions or comments that I think we have. So Jordan asks, do you have a weekly assignment this week? You do not. This week, we have the exam on Wednesday, which is why we're all here hanging out today. And then you are basically chemistry free until the videos will post like they always do, sometimes Friday through Saturday. And then you will pick back up with Alex on like Monday morning of like a week from now. So after we take the exam, you basically have 3 days to not think about this class before we pick back up next week. Does that make sense? So Destiny says you got a negative 1.977. Did you include the negative sign when you plugged it in? So hold on, I know. This equation has a negative sign in it, so it should be that you get a positive. So negative 2.18 e to the negative 18 multiplied by, open parentheses, 1 divided by squared, 1 divided by 3. Oh, shoot. So when I plug that in, I do not get that. So the negative sign times that equation. So Destiny, my guess, because you're getting the right number but the opposite sign. One thing that you could try, my guess is that you either forgot to add the negative 2.18 when you multiplied it, or have somehow gotten something kind of backwards with your 1 over 7 squared minus 1 over 3 squared. I usually do that first and then multiply that in my calculator. So this is like super kind of sketchy that we're going to do. And you know what? It's not going to work. I'm just going to put that down and we'll not look at my calculator on the YouTube Live. If you have questions, you can either send me an email with a picture of what you've typed in your calculator and I'll look at that. You can also pop into the SI session tomorrow and see if Megan can help you, or pop into my office hours on Wednesday and I'm happy to help you figure out how to use your calculator. Any other questions about this question? All right, that worked. Destiny, I'm glad it's a pretty simple thing, but I'll be honest, I lose my negative signs pretty often, and I try to be really understanding when that happens. So our next question, number 7, is draw the electron configuration of beryllium. How many valence electrons does it have? Write the electron configuration using the noble gas configuration. So when we look at our periodic table, beryllium is element 52. So this is element 52, which means it has 52 electrons, and it is Te. So when we look at this, we are basically going to draw out all of the orbitals. Now, different students have 2 different philosophies. Option number 1 is you can basically write 1s, 1, 2, 2s, and then add them in until you get to 52. I prefer to draw all of mine and then add in the electrons. So I'm going to erase this so that we can do all of that. my goodness. So from here, we're going to just start by writing them out. I think the thing that students get a little bogged down in is when we look at the periodic table, sometimes it gets kind of confusing. So the best thing to do is to remember that over here in these two are the s orbitals, p orbitals, d orbitals. And then I just kind of look at the beryllium and count the orbitals as I get down to that element. So I would look at the periodic table and say like, okay, we have a 1s, 2s, 2p, then we're going to have the 3s, followed by the 3p, followed by the 4s, 3d, whoops, 4p, 5s, 5, 4d, and then the 5p orbitals. Now, you can just go in and draw your arrows of, and don't forget Hund's rule, which says that we fill them all the same spin, then we go back, filling them the opposite spin, which I totally didn't use on the last one, but we will coming back here. I wish I could fast forward for you because I feel like this is super exciting to watch someone draw arrows all day, but we're almost to the end. So once we get here, there are 4 electrons in the p orbital. One thing I see students do a lot is they just fill them as pairs instead of remembering Hund's rule that says everybody gets an electron and then the last one goes in any orbital. Now, you could have put the one singular down arrow in any of the other orbitals. So you could write this or this. In fact, you could have flipped all of the orientations of those. You basically need 3 parallel and 1 non-parallel electron. So 2 singulars and 1 pair of them. So these are alternatives that I will erase just for clarity's sake. So the next part of the question asks how many valence electrons does it have? Valence electrons are the outermost shell. So in this case, valence is equal to the 5s plus the 5p, which equals 2, 4, 6 electrons. And so we will talk a lot more about valence electrons in chapter 8. So if today you're like, I don't quite remember this, that's okay. It's just a precursor. And so the next part of this equation asks us to write, using the noble gas configuration, the electron configuration. So this right here is the draw. If it says write, we're going to go ahead and write that out. So writing involves letters. And so the noble gas is the noble gas in the row above. It's always the row above. So in this case, it's going to be element krypton. So we're going to have open brackets Kr. So krypton has 36 electrons. And so we would see that right here. So this is Kr. And then we're going to have the 5s2, 4d10, and the 5p4. I will accept both. There are different schools of thought, and to be quite honest, both of them are mostly the same correct. Krypton. Okay. Terrible things are happening, guys. Awesome. Sometimes I feel super tech savvy, and some days I realize that I just like make things kind of go crazy. So you could also have written 4d10, 5s2, 5p4. And to be honest, these are both in my Gen Chem 1, not experience, but they are the same. In this case, in other cases, they are not the same, but I will accept both. They are equally correct. But you cannot rearrange them in a different order than these two. So what questions do you guys have about writing or drawing the electron configuration? Thanks, Nicole. So if you guys had looked at the worksheets, these were the only 7 questions I planned. I kind of thought they would take a little bit longer. So if you have other topics that we've talked about this semester, not this semester, sorry. In this section, we talked about, so in chapter 5, there were also molarity concentrations, there were oxidation numbers. We talked about, in chapter 5, we calculated delta H using several different methods. In chapter 6, we did a few other calculations. We talked about quantum numbers. What other topics do you guys have? And I'm happy to answer questions if you have any. If you don't, I don't have anything else prepared. So if you think of something else, I'm happy to answer it. Otherwise, I can let you guys go, not let you guys go early, but we'll stop this a little early, and so that will work for me. So other questions, or if you have none others, you can drop that. Can we do a heats of formation question? Sure. So this is not prepared, and so I am going to make it up, which means this may or may not be super awesome, but we can think about a heats of formation. So in this case, if we have a reaction where HCl plus NaOH goes to NaCl plus H2O. And these all have states, and the states are pretty important, so we'll add those in. From here, we would go into a table. And in this table, I am going to determine some values for HCl, NaOH, H2O, and NaCl. So this is negative 285. This is negative 117. So if these are our values in kilojoules per mole, to calculate delta H using the heats of formation, delta H reaction equals the sum of the delta H not F values for the products minus the sum of the delta H not F of the reactants. So from here, using my pretty fake values, you would basically just read the values and place them in. So it would be for NaCl negative 117 plus negative 285 minus negative 321 plus negative 98. So when we plug this into our calculator, we'll get negative 402 minus 1, which is negative 223. So negative 402 minus negative 223 gives us a delta H reaction of negative 179 kilojoules. So if by chance you had stoichiometric coefficients in there of any of these values, you would multiply the delta H naught F's for any value by that. So hypothetically, this balance equation is going to fall apart. But if we had a 2 here and a 3 here, you would then put a 3 here. Where did I put that? And put a, whoa, not in the right place. And put a 2 here. And then add those into your equation in that way. Does this make sense? I'm sorry it's not a technically correct, but it is in fact how you would set up and determine the answer. The other thing to note is, at least in these tables, it's possible that you could either not have a value, but that's only observed when something is likely in its standard state. So if you see O2 gas in the equation, the delta H naught F for that is 0, because that's how it's found in nature. And Jordan, if you have more questions about that, go ahead and write those in the comment box and I'll get to that. So David asks, I'm a little confused about acids and bases. To solve the neutralization problems, do we just remember what are strong and weak acids and bases? So if you're writing a acid and base neutralization question, I will mostly stick with the strong acids, because when the weak acids basically don't collapse, right? So we know in acetic acid, we see all three states. You see the acetic acid, the acetate ion, and the H+. All three of those are around all of the time. So we're going to leave the weak bases aside. You will probably talk about those a lot in lab. And if you take Gen Chem 2, you're going to talk about it a lot. But in this case, in this class, for a strong acid or a strong base, it basically breaks apart into its sections. You have the ionic, or basically the acid turns into an OH and a salt. That's the base. The acid turns into the H plus whatever the complex ion is. Once that happens, those will then break apart. And then from there, you can just do a metathesis reaction in that case. For the purposes of the exam, we are going to also assume that any acids in a titration question are strong acids or strong bases. And if you get confused about that, it should also have that information in the problem, just in case. But that's a good question. So Jordan asks, when do we use delta H? When do we use this equation? Delta H equals delta E plus P delta V. So for the most part, you would have to be thinking about a heat and a work equation. So we know that delta H equals Q, and we know that work equals negative P delta V. So in this case, this is a slight rearrangement of the delta E equals Q plus W. And so in this case, we would start to be able to see that. In the use of that equation, you would have to be provided some of these values. Either the ability to calculate delta E, and then the pressure and the change in volume, or something else. In Alex, they like to ask questions about this, where some of these are 0, and then you can basically extrapolate out that delta E equals negative P delta V or some such thing. But in a question, it would say the change of enthalpy, the change in energy at this pressure, and this change of volume. And then you could just use this as an algebraic type equation. Good question. What other questions do you guys have today? Are you guys ready for exam 2? It will be using the Respondus browser thing again, the same as it was last time. It really should run just the exact same as it did in September for exam 1. Everything should be the same, except for that weird timing thing. That's not going to happen again. But the rest of it, pretty much the same. Any other questions? Can I do a Hessel's law example? You know what? I will try. But it's going to take me just a second to write an equation. So delta H reaction. Thanks, Catherine. I think this is going to work. I'm not entirely certain. Hess's law are a little bit tricky, but the in this equation, what we'd like to do is be able to manipulate all of these equations into where we can be able to see this equation. So this will be delta H1, delta H2, and delta H3. So when we look at these equations, we can look at the first equation and see that all of the observed participants are in the right place. So we're going to keep number 1 the way it is. So A plus C goes to E, delta H1. For the second equation, this one right here, the F's need to be a product. And so we're going to flip that equation to where this is not going to work, but we're going to just figure that out as we go. C goes to 2F, which gives us negative delta H2. From here, when we look at this last one, B goes to half F. So in this case, we need 2B, so we're going to multiply this through by 2. That would give us 2B, gives us a singular F. So we're going to use 2 times delta H3. When we add these up, we would get A plus 2C plus 2B gives us E plus 3F. And then we would total up all of the delta H values. So delta H for the reaction is going to equal delta H1 plus negative delta H2 plus 2 times delta H3. Now, as I made this up on the fly, one thing you can see is that we have 2 C's on one side that are not supposed to be there at all. So there would be a way for us to set this up. And so instead of watching me attempt to do it again, on the exam, this would have worked out. But in a Hess's law equation, treat each equation one by one and basically manipulate them in that way. If you would like practice with that, there is another one in the chapter worksheets. There is also, I think I've selected a couple in the end of chapter list of problems out of the back of the book. And some of those will have an answer. So are there any other questions? David, do you have any other questions about this? I don't want to call it a mess of an example, but about Hess's law in general that I might be able to answer. Anybody else have any other questions, any different questions today? Give you guys a few more seconds. So if you're thinking of something and you're like, I just can't get out the words, go ahead and just hit like a wait into the comment box and I'll hang out for a few more seconds. Otherwise, oh, David, I'm glad that helped. Happy studying. If you have any other questions, feel free to send me an email. Feel free to pop into my office hours, which are on Wednesday from 1 to 2. The SI help sessions are tomorrow and Wednesday. I think she said that she's doing the same worksheet in both, but you'll have to check her email, which you can find in your Canvas account. So doesn't look like there are any other questions. If you guys have them. Oh, Jordan asks, will the materials from chapter 1 through 3 be on the exam? So by and large, no, yes. So I will not test you explicitly on material from chapter 1 or chapters 1 through 3. But the ability to balance a chemical equation was taught in chapter 3, but we're still going to use it. You may have to calculate the molecular weight, which we taught in chapter 3, but I'm not going to test you on that. So I'm not going to ask, let's see, the ability to calculate the atomic weight or limiting reactants are not going to be observed on this exam. But you might see other aspects of chapters 1 through 3 that are more like common chemistry themes, like balancing equations, naming we talked about in chapter 2, but you may need that in order to calculate some of these equations. Does that make sense? Any other questions today? Perfect. Y'all have a fantastic rest of your Monday. I will see you, well, I will not see you. On Wednesday, the exam opens a little bit before 2:45, and you'll be done 75 minutes after you start. Y'all have a fantastic Monday. Bye.